Welcome back to the deep dive, where we're once again taking the complexity out of your reading list and giving you that intellectual shortcut you need.
And if you've been following along with our source material, you know we've spent a good amount of time in the world of unsupervised learning.
That's right. It was all about density estimation. We were trying to figure out, how the data is structured, how those clouds of points are arranged in space, but without any labels.
We were essentially asking the data, tell me about yourself. What's your internal structure?
And we use some really powerful tools for that. Gaussian mixture models, k-nearest neighbors, but always in a purely descriptive way. We were just mapping the landscape.
Exactly. Well, today we close that chapter. We are moving into the final, and I'd say the defining part of this source material, supervised learning.
This feels like a big shift. We're moving from description to prediction.
It's the grand finale. We're going from asking, what is this data like? To, okay, given this data, what's going to happen next?
So our mission for this deep dive is to really get into the mathematical blueprints that make all of this work. We're going beyond just the buzzwords and looking at the why and the how. The math that lets us classify images or predict something like a stock price.
We're going to cover classification models. We'll talk about this idea of entropy as a map of uncertainty, and then we'll hit this really stunning realization that the simple least squares method is actually deeply fundamentally probabilistic.
So to start, the source material defines this new world very clearly. In supervised learning, our data isn't just a collection of feature vectors, X.
No, now it's a collection of pairs. We have X.
We have the answer key.
We have the answer key, exactly. The X is our data object, maybe a patient's medical stats, age, blood pressure, that sort of thing. And the Y is the discrete label.
So it could be sick or healthy, or if we're sorting colors, it could be red, green, blue.
And because we have these labels, our goal becomes really precise. It's quantifiable. We need to find a function, let's call it G, that maximizes what's called the a posteriori probability.
So that's P of Y equals Y given X. In plain English, what does that mean?
It means, given this specific patient's features, X, what is the most probable outcome, Y? Is it more likely they're sick or healthy? That's the question we have to answer.
And we're trying to learn this true probability distribution from a limited sample of data. So everything we're doing is really an approximation. We're learning the decision function to G.
That process, that learning, is the absolute heart of pretty much every supervised machine learning application running out there today.
Okay, so before we can build these predictive machines, we need a mathematical language, right? A way to handle these discrete labels. For two outcomes, we have the Bernoulli distribution. Sick or healthy, yes or no. Simple enough.
But what if you have more than two? What if you have, say, 3, 4, or M classes, like the primary colors you mentioned, or maybe 5 different types of defects coming off an assembly line?
We need a more general tool.
And that tool, which the source material defines in section 12.8, is the categorical distribution. It's really just a direct extension of the Bernoulli for more than 2 categories.
And the guiding characteristic here is this parameter vector, P.
Exactly. The vector P has M different probabilities, one for each class P1, P2, all the way to PM. And each PY is just the probability of picking that specific class Y.
And of course, the big constraint is they all have to sum to 1.
You have to land in one of the buckets. That's the only rule.
Now, if you look at the formal math for this in the source, it looks kind of terrifying. It has this big product symbol and an exponent inside these giant square brackets.
Ah, the Iverson bracket, or the indicator function.
Why make it look so complex for something that seems so simple?
It's purely for, let's call it computational elegance. It might look messy to a person, but to a computer program, it's like a perfect digital switchboard. Well, say you want the probability for class 3. The indicator function just makes sure that only the third probability, P3, is raised to the power of 1. All the other probabilities get raised to the power of 0.
And anything to the power of 0 is just 1. So they all disappear from the product.
They just vanished. So it's this very clever, computer-friendly way of just saying the probability of Y being Y is just P sub Y. The structure is really designed so that you can easily differentiate it and plug it into much larger, more complex models.
Okay, that makes sense. And this leads to what the source calls the core philosophical insight for all of classification.
Which is that we assume every single data object X that we look at has its own unique categorical distribution.
Wow, okay, so that parameter vector P is completely dependent on the input X.
Precisely. Think about a bank trying to assess loan risk. You have a young applicant, low income. Let's call that X young. The probability vector P might be, say, 80% high risk, 20% low risk.
But then an older applicant with great credit score comes in, a totally different X.
A totally different X and a dramatically different P. Maybe it's 5% high risk, 95% low risk. Our entire job, the whole point of classification, is to estimate this dependency. We're building a function that translates input features, X, directly into a probability vector, P.
And to do that, we're going to look at two big families of algorithms, the GMM-based classifier and the k-nearest neighbors classifier.
And the key thing is that both of them give us a probability, not just a hard yes or no.
Let's start with the GMM-based one. It seems like it all hinges on a single concept, Bayes' theorem.
It does. We want that a posteriori probability, P of y given X. Given the evidence, what's the probability of the class?
But that's really hard to calculate directly.
Almost impossible. Imagine trying to directly measure the chance a patient has a specific disease given their exact blood profile. The data is just too sparse. Bayes' theorem is like this intellectual cheat code. It lets us get P of y given X by using something much easier to measure.
The inverse relationship.
The inverse. The famous formula, P of y given X is proportional to F of X given Y times P of Y.
We can break that down into two ingredients we can actually handle. First, there's P of Y, the a priori probability.
Or the prior. This is just before we see any of the patient's data. How common is this class Y in general?
And the source says estimating this is almost trivial.
It's the easiest part of the whole puzzle. You just estimate it with relative frequency. You count how many items belong to class Y, n sub y, and you divide by the total number of items n.
So if 10% of our training data is sick patients, our prior probability for sick is just 0.1.
Exactly. Now for the second, much more interesting ingredient, F of X given Y, the class conditional density.
Also called the likelihood.
Right. And this asks the inverse question. If we already know someone is sick, what does the distribution of their features X look like?
It sounds like where the real engineering comes in.
It is, and this is where we connect right back to our journey with unsupervised learning. To model this, for each possible class Y, we model its feature distribution F of X given Y completely separately.
Okay, so if we're looking at, say, 4 types of product defects, A, B, C, and D, we literally split our training data into 4 separate piles.
4 piles. For the pile labeled A, you train one Gaussian mixture model. For pile B, you train a second GMM, which might be more or less complex. You end up with M distinct GMMs, each one trained on its own little subdata set.
So each GMM becomes like a probabilistic portrait of what the features X look like if the object belongs to that specific class.
That's a great way to put it, a probabilistic portrait. The GMM for defect A learns the typical measurements for that defect, while the GMM for defect B learns a totally separate pattern.
Once we have these M portraits, our GMMs and our M prior frequencies by Y, we're ready to go.
We've assembled the Bayes machine. A new unlabeled point X comes in. We plug it into that proportional formula for every single class, from 1 to M.
And the final decision function, G of X, is just the argmax.
Simple as that. You just pick the class Y that gives you the highest calculated probability. The denominator in the full Bayes formula, by the way, is just a normalization factor to make sure all those probabilities add up to 1. We often don't even need to calculate it to make the decision.
What's really cool is how flexible this framework is. The source highlights that you don't even need to use the same complexity for every class.
Right. If your defect A is really simple and uniform, maybe a single Gaussian, where k equals 1 is all you need. But if defect B has, say, 3 very distinct patterns, it forms 3 natural clusters.
You could use a GMM with k equals 3 components to model it properly.
Exactly. You tailor the complexity of your model to the complexity of the class itself.
But that flexibility brings us right to the classic machine learning dilemma, doesn't it? The complexity trade-off. The number of components k in our GMMs, that's our complexity dial.
It is. And if you choose a small k, the decision boundaries between the classes will be very smooth, very gentle. That's good because it reduces the chance of learning random noise.
But if the true boundary is actually really wiggly, a simple model might just miss the point entirely. It risks underfitting.
Systematically missing the true structure. Conversely, you could dial k way up, say 10 components for each class. Now the model has incredible expressive power. The decision boundaries can become super complex, winding all over the place.
It can adapt to almost any shape you throw at it.
But the danger is huge. You risk the model starting to learn the noise instead of the real underlying pattern. The source material shows these great examples of what happens. You get these little isolated islands of one class deep inside another's territory.
Why does that happen?
Because the model used a tiny little Gaussian component to perfectly fit a few random outliers. That's the classic signature of overfitting. The model is too nervous, too sensitive, and it sacrificed its ability to generalize just to get a perfect score on the training data.
So finding that Goldilocks number for K is the real art here. Not too simple, not too complex.
And it's usually an empirical exercise. You try different values, you use cross-validation, but it's all governed by this fundamental trade-off.
Okay, let's pivot to the second major approach, the K-nearest neighbors classifier. This one feels, I don't know, maybe the most intuitive method we've talked about.
It is brilliantly simple. You have a new point X, you don't know its class, you just forget all the complex modeling, and you ask the data itself, who are your closest friends?
So you draw a sphere around the new point and just expand it until you've got the K closest data points from your training set, your K neighbors.
And then you just hold a vote. It's pure democracy. You count how many of those K neighbors belong to Class A, how many to Class B, and so on. The majority wins.
It's like tribal politics for data points.
It is. But what's really amazing is the clean mathematical reason for why this works. It's not just a cute trick. When you take the density estimates from the KNN rule and plug them into Bayes' theorem, a whole lot of stuff just cancels out.
Okay, you have to walk us through that. That sounds like magic.
It feels like it. So remember how we used KNN for density estimation? We estimated the class conditional density f of x given y by counting the points of that class, k sub y, inside a volume V, and then dividing by the total number of points of that class n the volume.
Right, and the overall density f of x was the total count k inside V divided by the total number of points n in the volume V.
Okay. And we also know the prior probability, p of y, is just n sub y over n. Now, you took all three of those pieces and you substitute them back into the Bayes formula for p of y given x.
And what happens?
Well, the volume term v is in both the numerator and the denominator, so it cancels. The total sample size n cancels. The class-specific total ny also canceled out.
It all just disappears.
It collapses. The final simplification is just breathtakingly simple.
It becomes p of y given x is approximately k sub y divided by k.
That's it. The probability that your new point belongs to class Y is simply the fraction of its K neighbors that already belong to class Y. So that democratic vote isn't just an intuitive hack. It is the mathematically justified way to estimate the a posteriori probability using local data density.
That's incredible. So the decision rule is just find the class with the most friends in your neighborhood.
Yeah. Let's think about the most extreme case when K equals 1. The next neighbor rule.
The tiny dictator scenario.
Right. The new point X just takes on the class of its single closest neighbor. No consultation, no vote. It's as local as you can possibly get.
And visually, this does something really dramatic to the feature space. The source points out that the decision boundaries for K equals 1 are the exact perpendicular bisectors between the training points.
If you have a red point and a blue point right next to each other, the boundary is the line that is exactly equidistant from both. This carves up the entire space into these Voronoi cells.
Like a mosaic.
A complex, jagged mosaic. Every point inside one of those cells is closest to the single training point that defines that cell.
And just like with the GMMs, K is our complexity lever here. It controls that same trade-off.
With K equals 1, complexity is maxed out. The boundaries are nervous, jagged, super sensitive to outliers. If one red point accidentally gets recorded deep in blue territory...
The K equals 1 rule gives it its own tiny little kingdom, its own Voronoi cell.
It does, and that is classic overfitting. You're learning the noise, not the signal.
But if you pick a really big K, like 100, you smooth everything out.
Dramatically. The model starts to ignore those local details and just focuses on the big picture. You reduce the risk of overfitting, for sure, but you increase the risk of underfitting, where you smooth over important fine-grained structures that are actually real.
So again, you have to find that optimal neighborhood size. Too small, you're sensitive to noise. Too big, you blur out the detail.
The eternal struggle.
What I really love about this section of the source, though, is the KNN paradox. It's this amazing theoretical result.
It's fantastic. It basically says that even though K equals 1 seems so noisy and unstable, as your amount of data, n, goes to infinity.
Asymptotically.
Asymptotically, the simple k=1 classifier is nearly perfect. Its maximum error rate is mathematically proven to be no more than twice the error rate of the absolute best, godlike, perfect Bayes classifier.
For such a simple rule, that's a stunning guarantee.
It's a non-parametric rule. It needs no training, just memory. And it's that good. It's amazing.
So why doesn't everyone just use k=1 all the time? There has to be a catch.
Oh, there's a massive catch, a huge practical price tag. Unlike the GMM classifier, which trains for a while and then boils all the data down into a few parameters, the means, the covariances.
KNN has to remember everything.
It has to store the entire training data set, D, forever. And for every single new prediction you want to make, you have to search through maybe millions or billions of stored points just to find the K closest ones.
The computational cost must be insane.
It's prohibitive for large data sets. It just doesn't scale well. That's why, in practice, you have to use these specialized data structures. The source mentions KD trees.
K-dimensional trees.
Right. They're these clever ways of organizing the data in space so you can very quickly rule out huge regions that couldn't possibly contain the nearest neighbors. It speeds up the search, but that fundamental need for memory in search is always going to be its main limitation.
Okay, so we've seen how classifiers make decisions, how they assign probabilities. But the probability alone isn't really the full story, is it?
No, not at all. There's a world of difference between a system saying, I think this is Class A with 51% probability, and another saying, this is Class A, 99% probability.
In both cases, the hard decision is A. But the confidence level is completely different.
And being able to quantify that doubt, that uncertainty, is absolutely essential if you want to build systems that people can trust. If your self-driving car's classifier says, that's a pedestrian 52% sure, you want a giant red warning light to go off.
But if it says 99% sure, you can trust the decision. We need a way to measure this uncertainty.
And that's where entropy comes in. H of x, as it's defined in the source.
The formula is the negative sum of p of xi times log base 2 of p of xi. How do we understand that intuitively?
You have to go back to Claude Shannon, the father of information theory. He's the one who came up with it.
And what was his goal?
Shannon said that entropy measures the average amount of information, or surprise, in a message. Think about the probabilities. If an event is super rare, p is almost 0, and then it happens, you're very surprised. It carries a lot of information.
And the logarithm of a number close to 0 is a big negative number.
And that negative sign out front flips it to a big positive value, maximum surprise.
And if an event is certain, if p=1.
The log of 1 is 0. 0 surprise, 0 information. If someone tells you the sun will rise tomorrow, they've given you 0 bits of information. You already knew that.
So high entropy means a high average amount of surprise. And in the context of our classifier, that means maximum confusion.
That's it, exactly. The uncertainty is at its absolute maximum when the classifier is totally confused and just assigns equal probability 1 over m to all m classes. It's basically just guessing.
And the uncertainty is minimal 0 when it's 100% certain. P=1 for one class, 0 for all the others.
Right. And to make this a practical tool, especially if you're comparing, say, a 2-class problem to a 50-class problem, the source suggests that we normalize it.
How do we do that?
You just take the entropy, h, and you divide it by the maximum possible entropy for that problem, which is always log base 2 of m.
And that gives us a normalized entropy, h norm, that always goes from 0 to 1.
Always. 0 is total certainty. 1 is total confusion, maximum guessing. This is the critical warning lamp that we need for our systems.
A high normalized entropy is a signal.
It's a signal that the input data x is in a region of the feature space where the model is fundamentally unsure of itself. The computer shouldn't just spit out the majority class. It needs to flag that uncertainty and ask for help, maybe from a human.
Especially in high-stakes applications, like a medical diagnosis. The uncertainty score is almost more valuable than the prediction itself.
I would argue it is more valuable.
The visualization in the source material for this is fantastic. It literally draws a land map of doubt over the feature space.
It's a great way to connect the abstract math to the actual geometry of the problem. In regions far from any decision boundary where one class is clearly dominant, the model is very certain.
So entropy is near 0. Maybe those are the light-colored areas on the map.
Exactly. But right along the decision boundary, that front line between Class A and Class B, the model is torn. The probabilities are close to 50-50.
That's where P of y is close to 1 over m for multiple classes.
And that is where your entropy is maximal. So that region of maximum confusion shows up as this dark band on the map. It tells you exactly where the model is strong, where it's weak, and crucially, where you should probably go get more data to help it make up its mind.
The map of doubt is just as important as the map of decisions. I like that.
I think it's fundamental.
Okay, let's make our final big transition. We're moving from the discrete world of classification, is it A or B, to the last major pillar of supervised learning, regression.
So now, the target variable y is no longer a discrete class. It's a continuous, real number.
We're going from, is this house a good investment, to, what is the exact price of this house in dollars? Or from, is the car's braking distance too long, to, what is the precise braking distance in meters?
We're still looking for a function h of x, but now that function has to output the expected mean value of that continuous variable y.
The big conceptual shift here seems to be how we model the uncertainty. In classification, we were modeling the probability of the class. Here, we're modeling the error, the noise.
That's right. The standard stochastic model, which the source lays out very clearly, is that y equals h of x plus epsilon. The value you actually observe, y, is the true underlying function h of x plus some random error term, epsilon.
We're acknowledging that the real world is noisy. Measurements are never perfect.
And we have to make an assumption about that noise, about epsilon.
What's the standard assumption?
We assume the noise is normally distributed. It follows a Gaussian curve, centered at 0, with some variance, sigma squared. This means the probability of seeing any specific y is highest right on our prediction curve, h of x, and it falls off symmetrically the further away you get.
So our prediction curve, h of x, is really the mean of an infinite number of little Gaussian probability distributions, one for every possible input x.
That's a perfect way to visualize it. And to start, we're going to use the simplest possible model for h of x, linear regression. So h of x equals x transpose theta. We're just trying to find the best slope, theta hat, to fit a line or a plane through our data cloud.
So we need a rigorous way to define best fit. How do we find that optimal slope, theta hat?
We go right back to our most fundamental tool, maximum likelihood. We want to find the parameters, theta, that make the data we've actually observed the most likely to have occurred, given our model.
And since we assume Gaussian noise, our likelihood function, L of theta, is the product of all the Gaussian probability densities for all n of our data points.
Exactly. And if you look closely at the exponent in that Gaussian formula, the most important part is related to the squared error. The observed value, ym on, minus our prediction, h of x on, all squared.
This is where it all comes together.
This is where the profound connection is made. To maximize the likelihood, which is a product of these densities, we need to maximize the exponent. Or, more precisely, we need to minimize the negative of the exponent. And that naturally focuses the entire process on minimizing that squared difference term.
And this is what the source calls the great aha moment for this whole field. We take the negative logarithm of the likelihood function.
The negative log likelihood. The logarithm does two beautiful things. First, it turns that messy product in probabilities into a nice, clean sum of log probabilities, much easier to work with.
And second,
when we're trying to find the minimum of this function, any terms that don't involve our parameter theta things, like the constants with 2 pi or the noise variance sigma squared, we can just group them together and ignore them. They shift the whole function up or down, but they don't change where the minimum is.
and what's left after you strip all that away?
What's left is a function that is proportional only to the sum of the squared errors, the sum of yn minus prediction squared.
So the conclusion is, maximizing the likelihood function under the assumption of Gaussian noise is mathematically identical to minimizing the sum of squared errors.
It is the exact same problem. This is the famous least squares method, which Gauss came up with intuitively centuries ago.
So we didn't just pick these squares because it's easy. We use it because modern probability theory confirms that under the most common model for noise, it is the most probable answer. It is the statistically optimal thing to do.
It's not a coincidence, it's an identity. And this gives us this amazing analytical simplicity. When you write that error function down using compact matrix notation,
The norm of y minus x theta squared,
right, you immediately recognize its structure. It's a quadratic function in our parameters, theta.
which means the air surface looks like a big bowl, a paraboloid.
And the best news in the world about a clean quadratic bowl is that it has one single unique global minimum. There's no risk of our algorithm getting stuck in some other little local dip, which is a huge problem for iterative methods like the EM algorithm we use for GMMs. Here, we just need to find the bottom of that one bowl.
And if you have a smooth bowl, you can find the bottom using calculus. You find the derivative, you set it to 0, and you solve.
Exactly. Since theta is a vector, we need to use vector calculus, but the principle is the same. The source shows we only need two main rules for this derivation, which are basically just analogs for differentiating linear and quadratic terms with matrices.
We take our squared error function, expand it out into 3 matrix terms, and then differentiate each one with respect to theta.
And the differentiation is surprisingly clean. The term with y transposia is a constant, so it just disappears. The linear term gives us minus 2 x transpose y, and the quadratic term gives us plus 2 x transpose x theta.
We take that whole thing, the gradient, and set it to the 0 vector.
That finds the critical point, which we know is the bottom of the bowl. We can cancel out the constant 2 punt, which leaves us with minus x transpose y plus x transpose x theta hat equals 0.
You rearrange that, and you get the famous normal equation. X transpose x theta hat equals x transpose y.
This is the moment of triumph. To solve for our optimal parameter vector theta hat, all we have to do is pre-multiply both sides by the inverse of that matrix, x transpose x.
The final solution, theta hat equals x transpose x inverse times x transpose y. The whole problem is solved in a single calculation. No iterations, no waiting. It's an analytical solution.
That's a rare luxury in machine learning. It's beautiful, but there are some practical catches.
Of course.
For that inverse to even exist, the matrix x transpose x has to be invertible. It has to have full rank.
When would it not?
It would fail if your features are linearly dependent. Say you include two features in your model, and one is just a multiple of the other, like measuring temperature in both Celsius and Kelvin. The information is redundant.
That makes the matrix singular.
And the whole calculation breaks down. So you have to be careful to select non-redundant features. Also, in practice, actually calculating a matrix inverse can be numerically unstable, so real software usually solves the linear system with more robust methods like QR decomposition. But the formula is the foundation.
Okay, so this linear model is analytically perfect, but it's linear.
Yeah.
It can only model straight lines or flat planes. What if we're trying to model something that's inherently curved, like the braking distance of a car, which grows quadratically with speed?
A straight line is going to fail completely. We need curves. But we just went through all this beautiful work to derive the normal equation. We don't want to throw away our guaranteed analytical solution.
So we need a way to model nonlinear data without losing the mathematical linearity of the system.
And the solution is absolutely ingenious. It's the basis function trick. Let's call it phi of x.
What's the core idea?
The idea is to transform our input data, x, into a new, often higher dimensional space, phi of x, where the relationship becomes linear again.
So our model changes from h of x equals x transpose theta to h of x equals phi of x transpose theta.
Right. We take our original input x, we pass it through this transformation phi, and we get a new expanded feature vector.
So even though the relationship between the original input x and the output y is now curved,
the relationship between the transformed input, phi of x, and our parameters, theta, is still just a simple weighted sum. It is still linear in the parameters.
and because it's linear in theta, all the math we just did, the entire normal equation derivation, still works perfectly.
Perfectly. It's this simple substitution that gives us immense modeling power without having to resort to messy iterative optimization methods.
Let's use the classic example from the source. Polynomial regression. We want to fit a parabola, a grade 2 curve.
So we need to transform our single input x. Our transformation, phi of x, would become a vector with 3 parts, 1x and x squared.
And our parameter vector theta now also has 3 weights to learn. Theta 0, theta 1, and theta 2.
And the resulting model h of x equals theta 0 times 1 plus theta 1 times x plus theta 2 times x squared is a parabola.
And that constant 1 as the first basis function is really important, isn't it?
It is essential. That's what allows the model to learn the y-intercept. Without it, your curve would be forced to go through the origin, which severely limits its ability to fit real data.
So the formula for the optimal solution is exactly the same. We just replaced the original data matrix X with our new expanded feature matrix phi.
The structure is identical. Theta hat equals phi transpose phi inverse times phi transpose y. That term in the parentheses is often called the pseudo-inverse of phi. This trick is why linear algebra is still the absolute backbone of so much of classical machine learning.
But with great power comes, well, a great potential downside. This flexibility from high-grade polynomials opens up a huge risk, overfitting.
It does, and the source uses this brilliant example of fitting a noisy cosine curve to illustrate the critical trade-off between bias and variance.
Okay, so imagine we have 20 data points. They're sampled from a smooth cosine wave, but each point has a little bit of random Gaussian noise added to it, a typical real-world measurement problem.
Right. Now, what happens if we try to fit this data with a low-grade polynomial? Say, grade 2, a simple parabola.
Well, the model is just too stiff.
It has high bias. It systematically misses the underlying function because a parabola just can't model a wave. It's underfitting. It's too simple for the job.
Then there's the grade 4 polynomial in the middle of the illustration. That looks like the optimal solution.
The Goldilocks solution. It's flexible enough to capture the general wave shape, but it's rigid enough that it ignores most of that random noise on the data points. It gets the trend right.
Okay, now for the crazy one. The grade 19 polynomial. We have 20 data points, and we're using 20 parameters to fit them. The intercept plus all the powers of x up to x to the 19th.
This creates perfect interpolation. Because you have exactly one parameter for every single data point, the curve is mathematically guaranteed to pass exactly through every single one of those blue crosses.
The training error is 0.
The training error is 0. And while that sounds perfect, in machine learning, that is a giant flashing red warning sign. This is the definition of dangerous overfitting.
The model now has high variance.
Exactly. It hasn't learned the underlying cosine function. It has learned the noise. The curve it produces swings wildly between the data points. It's incredibly sensitive to the exact location of each noisy point.
It looks like this frantic, brittle wire that's trying to connect every dot perfectly.
And if you were to give this model a new, unseen data point, its prediction would be wildly inaccurate because it's basically just predicting based on memorized noise. It can't generalize.
That's such a profound insight. Achieving 0 training error means you have literally built the measurement errors and the random noise directly into your prediction function.
It's like a student who has memorized the answers to every question on past exams but understands none of the principles. Faced with a new question, they're completely lost. Generalization is always the goal, not perfect memorization.
Plus, the source points out a practical danger, right? Calculating x to the 19th power can create massive numbers, which leads to numerical instability and rounding errors in the computer.
So overfitting isn't just a statistical problem, it's an engineering problem too.
Okay, one last piece of the puzzle. We can't just assume we know the noise variance, sigma squared. We have to estimate it from the data itself.
Right. And since we use maximum likelihood to get our parameters theta, we can use maximum likelihood to get sigma squared as well. We just take that log likelihood function and differentiate it with respect to sigma squared instead of theta.
You set the derivative to 0, you solve.
And the result is beautifully simple and self-referential. The optimal estimate for the noise variance, sigma hat squared, turns out to be 1 over n times the sum of the squared deviations between the true I values and our model's predictions.
So, the best estimate for the noise variance is just the mean squared error of our model on the training data.
It closes the loop perfectly. We use least squares to find the best theta, and then we use the squared error from that best theta to estimate the variance of the noise itself.
Now let's go back to the cosine curve one last time. We can draw an uncertainty tube around our prediction curve using plus or minus our estimated standard deviation, sigma hat.
For the underfitted grade 2 parabola, the model knows it's missing the data badly. The squared errors are huge, so the estimated sigma hat is large. The uncertainty tube is wide.
For the optimal grade 4 model, the tube shrinks to a realistic level. It accurately reflects the real random scatter of the data around the true curve.
But now look at the overfitted grade 19 interpolator. Because the curve goes almost perfectly through every single data point, the sum of squared errors is almost 0.
Which means our estimated noise variance, sigma hat squared, also shrinks almost to 0.
And this is the final and maybe the most important warning of this entire deep dive. The model is hallucinating certainty. It has 0 training error, so it calculates that there is 0 noise. It is massively underestimating the true uncertainty because it baked the noise right into the curve itself.
A zero-error model is often the most dangerously overconfident model you can possibly build.
Absolutely.
Wow. So that brings us to the end of this incredibly dense journey. We've really covered the 3 fundamental pillars of classical machine learning, all of them rooted in stochastics: density estimation, classification, and regression.
And yet, as the final diagram in our source material shows, we've really only been exploring one branch of the family tree, what it calls classical learning. We've been dealing with explicit functions, linear algebra, things with nice analytical solutions like the normal equation.
But there's this whole other world on the left side of that map: deep learning. The famous neural networks, CNNs, for images, RNNs, and transformers for language.
And mathematically, you can think of a deep neural network as just a very, very complex chain of these basis functions and nonlinear transformations with maybe billions of parameters. And because they're so complex, you can't just solve for the answer with a normal equation.
You have to find the best parameters iteratively, using methods like gradient descent.
But even that process, stochastic optimization, relies on the exact same principles of calculus and probability that we've been discussing. The bedrock of stochastics is still there.
And beyond supervised and unsupervised, there's reinforcement learning, and AI learning to play Go or chess through trial and error.
Learning by interaction, by getting rewards and penalties, not by being shown labeled data. But it's still a system that is stochastically optimizing its behavior to maximize its expected reward over time. Every single branch on that tree grows from the same mathematical soil.
For those of you listening who really want to dig deeper now, the source recommends 2 fantastic next steps. First, the book Mathematics for Machine Learning.
That is the perfect bridge. It's designed specifically to connect the fundamentals, linear algebra, probability optimization, directly to how modern machine learning algorithms are actually built.
And the second recommendation is the classic text, Pattern Recognition in Machine Learning, by Christopher Bishop.
If you want the deep, deep dive, the mathematically rigorous foundation for all of this, especially the Bayesian and probabilistic frameworks, Bishop is the definitive reference.
So as we close the book on this source material, what's the one core insight that holds it all together?
I think it's that stochastics isn't about giving up and surrendering to randomness. It's the opposite. It's the scientific framework for mastering uncertainty, for finding the patterns in the chaos, and for making rational, sound decisions in a noisy world.
Which leads us to our final provocative thought. We learned today that the perfect fit, that zero training error from the grade 19 polynomial, is usually a lie. It leads to this dangerous overconfidence, this hallucinated certainty.
So here's the question. If the ultimate goal of AI is not just accuracy, but trust, should we be prioritizing robust models that are honest about their uncertainty, even if they sometimes get a training point wrong, over these perfectly interpolating models that are brittle, overconfident, and can be wildly wrong when they face something new? The future of trustworthy and responsible AI really depends on how we answer that question.
A profound challenge to think about. Thank you for joining us on this deep dive into the mathematical blueprint of supervised learning. We'll see you next time.